Example 6. Suppose the side length of a cube is measured to be 5 centimeters with an accuracy of 0.1 centimeters. First, we want to use differentials to estimate the area, or the error, in the computed volume of the cube. So, how we're going to do this is first, note that volume of a cube is going to be the formula x cubed. This tells us that dv, here's where our differentials come in, is equal to 3x squared dx. Now, because our dx, okay, that is our predicted accuracy, or rather our inaccuracy, because that is between 0.01 and negative 0.01, we can then predict that dv is going to be between 3x squared. Well, our actual measurement is 5 centimeters, so 5 squared times dx, which on this end of our inequality is 0.1, and dv, the lower bound, is 3 times 5 squared times negative 0.1, meaning that dv is between negative 7.5 and positive 7.5. So the predicted error is within 7.5 units cubed for our volume. Now let's actually compute the volume if the side length is that 0.1 in either direction, and so that we can compare what we just estimated, okay, our error to be 7.5 centimeters cubed, with the actual potential error. Right, so our x, our side length, is between 5.1 and 4.9 centimeters, based on what we just stated there, which means that our volume, okay, because our volume is x cubed, our volume is between 5.1 cubed and 4.9 cubed, which comes out to be 117.649 centimeters cubed and 132.651 centimeters cubed. Now, because the actual volume is 125 centimeters cubed, our error, we'll label that as delta V. So subtracting 125 from each of these, we find that our actual error in volume is between 7.651 and negative 7.351. which is very close to that predicted 7.5 on either side as an estimated error. All right, for our next question, we have an astronaut using a camera to measure the radius of Earth as 4,000 miles with an error of plus or minus 80 miles. We'll use differentials to estimate the relative and percentage error, and then we'll go from there. So first, we have that our relative error is defined as dq over q for some quantity q. So in our case, that will be dv divided by v. Okay, I don't need an approximate there. For us, that will be dv divided by v. All right, and now we have our volume, because this is a sphere. We're assuming that the planet is a perfect sphere. That is 4/3 pi r cubed, meaning that dv is equal to 4 pi r squared dr. Now we're given the error. We're given the error for our radius of the planet as plus or minus 80 miles. So dr is between 80 and negative 80, putting our dv, let's do that over here, putting our dv bound between 4 pi 80 squared times dr. Oh, actually, the 80 does not go there because the Earth's radius is 4,000. Okay, and then dr is the 80. Okay, and that's between the lower bound is 4 pi 4,000 squared times negative 80, meaning, well, actually let's not evaluate that at this point, because what we need to do next is divide by v. Now, because v is 4/3 pi r cubed, I'm going to write this as 4/3 pi times 4,000 cubed on both sides. Alright, now dividing each of the expressions, we find that dv over v is bound between 0.6 and negative 0.6, meaning that our relative error is 0.06. Our relative error is 0.06, which means that our percent error is 6%.